Hi everyone. The topic of today's lecture is short channel effects for MOSFET transistors. So the two kinds of short channel effects that we will be discussing today are DIBL or drain induced barrier loading and subthreshold slope. So the first question that arises is, why do we care about short channel effects in MOS devices, CMOS devices? So to understand that, let's look at a representative uh, circuit, which is say an inverter, and I will draw a P diffusion and N diffusion on a layout. And if we have a poly or a gate, which looks like this, which is the input node, and there is an output node, which is this, which is say TCN, right, or an O1, right, and this would be the power supplies for the two. So this is P, this is N, right? Now, what the Moore's law says is to be able to shrink the circuit, you can either shrink it in the X direction or you can shrink it in the Y direction. Short channel effects are related to the X direction shrinking, which means you want to be able to fit more and more of such circuits in the X direction. Now, how would we go about shrinking the circuit? Invariably, one of the most important things that comes about is you want to be able to shrink this part of the device, which is the gate length. Now, if I were to draw a cross section of this device, um, it would look something like this. Um, so this is the gate length, which we need to shrink to be able to fit more transistors in the same given area. And this is the effective channel length, which controls how the transistor behaves. And as the gate length shrinks, the effective channel length mostly shrinks. Almost always it ends up shrinking. And the reduction of effective channel length is the reason why short channel effects come into play. So uh, degradation of short channel effects is, it goes hand in hand with shrinking the gate length of the device. Now, if you want to know why does this happen on a physical level, the way we can think about um, is a potential landscape for say electrons, which are the carriers. This is the potential barrier that they see in the off state. And that's the reason why they're not able to cross the channel region, which is being able to go from the source to the drain side, because there is a barrier that has been created by the gate, which is sitting above the channel region, right? Now, because of this barrier, they have to be able to climb this barrier to be able to reach the drain. Now, what happens is, as the L effective reduces, the drain is able to exert an electric field which is so strong that it's able to circumvent the electric field that the gate creates vertically down, and the drain is able to directly talk to the source, and the gate is not able to control that communication between the drain and the source. Now, on this potential landscape, what it means is that this barrier starts looking more like this, right? So essentially there is a reduction in the barrier height, and these carriers are able to reach across to the drain more easily, right? And that is what is called drain induced barrier lowering, right? Um, so if we want to understand how can we look at this short channel effect on a measurement level, the way people do it is by looking at the drain current on a logarithmic scale. And I shall be drawing this graph again and again because this is the most important graph to look at when we are talking about short channel effects, which is look at the log of the current, plot it against the gate voltage, and look at two conditions. One is drain, which is low drain, and one is a condition where the drain is high voltage, right? And what they look like is for the low VD, the curve looks like this. For the high VD, the curve looks like this, right? So this is for this curve, this is for this one, right? Now, what is DIBL on this graph? DIBL is we pick a particular drain current and we figure out what is the delta between these two curves. And DIBL is the amount of delta VG that is between these curves for a given current for the delta VD that we applied. And delta VG is in millivolts, delta VD is in volts. So the units of Dibble or DIBL are in millivolts per volt. So we can easily say that if we want to plot something which is DIBL equals 0, that curve, these two curves in that case should look pretty much overlapping in this part, but they should exactly match in the leakage condition or the condition which we are interested in, and they will look pretty much like this, right? This is the case of DIBL equals 0. Now, for most devices that we care about in today's world, DIBL is almost never 0, but we wish that the DIBL gets closer and closer to 0. So the good values for DIBL that people look for are anywhere between the range of 40 to 70 millivolts per volt. That's a good DIBL. And a bad DIBL would be in anything beyond that. There is no hard and fast rule of what exact number is called a bad DIBL. It just depends on what can be sustained by the technology, right? Now, as I mentioned that DIBL is one of the short channel effects, and hand in hand goes the other short channel effects, which is called the subthreshold slope. So I'm drawing the same curve again. Now I'll point to a different part of the curve, which is the slope of these two, right? So the slope of these two curves, this one is called subthreshold slope high or SAT, subthreshold SAT, and this is called subthreshold slope lin, because this is in saturation when the drain is high, this is in linear when it's low. And subthreshold slope and DIBL tend to go together for most of the cases, which means that if the short channel effects are bad, Dibble goes high and subthreshold slope goes high. So for subthreshold slope, for a silicon device at room temperature, the minimum value the subthreshold slope can go to is 60. And the units for that are millivolts per decade. What that means is how much is the delta VG that is needed to get a decade change in the ID, right? Or a 10x change in ID. How much delta VG do we need? That slope is called subthreshold slope. So what does a good subthreshold slope look like? A good subthreshold slope would look like this. A bad subthreshold slope would look like this, right? So our endeavor is that the device should turn on instantaneously, right? So it should be able to go from this leakage current scenario to the on-state scenario in a very quick, smallest VG possible. And in this case, when it's relatively flat, it means the device is turning on very slowly. and hence it means it's a bad subthreshold slope. So anything that goes, say, above 80 millivolts per decade is a bad subthreshold slope. Okay, now let's keep moving on to the next part of this discussion, which is um, why do we, how does the short channel effect affect the performance of the device, right? So how does it matter if, say, DIBL or DIBL is bad, right? So let me create a curve with a bad DIBL device, which looks like this, and I'm only plotting of the VD of 1 volt in this case, right? Now, this point that I'm highlighting here is what is called the off-state current, I off, usually in nanoamps. So there are strict requirements for any technology of what this I off needs to be. And uh, if this leakage current is high, it tends to cause high leakage power, which is not a good thing. So let's say in this technology, the leakage current needed to be at this point, right? And because of the short channel effect being bad, it ended up being at this point, right? So what are the choices that a device designer have um, to be able to bring the leakage current down, right? The one thing that he can do, which is of course advisable, is to make the short channel effect good, which will make the curve look something like this, right? And there is another case that he can do, which is, let's say the short channel effects cannot be improved. In that case, he can shift this curve laterally using what is called a work function, or the metal gate barrier profile, right? So if this thing is shifted, the curve shifts laterally. What that means is that this curve will now start to look more like this. So I will draw a dashed line for that. Correct? So in both cases, with a good short channel effect and a bad short channel effect, we finally managed to reach the same leakage condition, right? Then the question is, what did we lose, right? And to be able to understand what we lost by going to a bad short channel effect device and push the gate work function or the threshold voltage to be high is, we can see that in a linear scale. So let's draw the linear scale for this graph and how that would look like. Okay. Okay. So when we look at it in the linear scale, the curve will look something like this. So now it's ID versus VG, right? And I will first draw the case where I have a good short channel device and the curve looks, let's say, something like this, right? Now I will draw the bad short channel effect device and that will look like this. Right? So notice how the threshold voltage of the poor short channel effect device. So by the way, threshold voltage, which is also called VT, is the point at which the device starts conducting a lot of current, right? And it's an important figure of merit. So what we've ended up doing is, because we increased the work function to be able to match the leakage that was needed by the technology, we ended up increasing the threshold voltage of this device. And what that meant was, if we want to look at the on-state current, now we're concerned about the on-state current because we've ended up matching the off-state current. The on-state current between a good short channel device and a poor short channel device is quite big, especially near the threshold voltage. So let's say this is the threshold voltage of the bad device, this is of the good device. So around the around the threshold voltage point, there's a big gap between the two devices. what we see is that that gap starts lowering as we go to higher gate voltages. So what it means is for VG, which is say around VT threshold voltage plus zero point 0.2 to zero point 0.5 volts, right? This effect is very severe, correct? And if you go to a big VG point, which is say VT plus 1 volt, the effect is not as significant, right? Now the question is, why do we care about the operating point of the gate voltage near the threshold voltage? And that has to come down to how, as the Moore's law has scaled, the way to reduce the dynamic power of a circuit, which is given by the capacitance of the devices, times the supply voltage squared, right? So usually the technologists have been scaling this VDD down more and more. And what that implies to be able to reduce the dynamic power. What that implies is low gate voltages, which are especially near the VT point, are the most vulnerable. If they degrade, the performance, which is ID on, suffers the most. And hence we care about low VG points near the VT a lot more, because the VDD has been constantly going down. And hence the short channel effects can really degrade a device, because we can somehow reach the off state current by changing the VT or the work function. But in that process, we end up losing the on state current. And that on state current is the biggest thing that helps us drive the circuits faster, right? So that's really uh, what happens when we have so let me show. So this is the poor short channel device, short channel effects device, and this is the good one, correct? Now one more thing to mention is um, if we want to continue to improve the short channels, what are the device related tricks that people do, right? In terms of the architecture of the device, this is the main reason why people have gone from what used to be the planar devices, where there was a single gate that would control this region, which is the channel between the source and the drain. That has been slowly moving on to what became a FinFET device, right? So I'm drawing the gate that now surrounds um, so this would be the source, this would be the drain. And now the gate is controlling this part of the fin, this part, and also on the other side, which I'm not showing. So essentially, instead of just one side being controlled by the gate, the gate is wrapping around the fin, and it helps control the short channel between the source drain a lot. And this has what has morphed into the all-sided gate control, which is also called the nanosheet. So this would be, say, the silicon nanosheet, and the gate would be all around that transistor, right? So that's how the technology has been evolving from planar transistor to the FinFET to the gate all around. And the biggest reason is to be able to control these short channel effects from going bad when the gate length is to be shrunk, correct? So now let's keep moving to some more concepts. Uh, so as you remember, I mentioned that the DIBL, DIBL, and SS tend to go together most of the times. So what are the scenarios in which they don't go together? In what that means is, let's say the subthreshold slope degraded, but we didn't see a big enough effect on the DIBL. Some of those scenarios happen when, let me draw a picture here. One case could be an effect which is called GIDL or GIDL. So this is the subthreshold slope, as I mentioned, right? So I'm still drawing the log ID versus VG. There is an effect which is called gate induced drain leakage. That tends to happen when the VD is high and the VG is very low. Because of that, this curve starts to creep up at this point. And this also impacts the slope here, right? Now, in this case, the DIBL, which is measured more closer to the on state, is not impacted as much, but the subthreshold slope is impacted heavily. So this would be one case where the subthreshold slope goes high because of this effect. And we will talk about this in another lecture in detail, where subthreshold slope would be impacted much more, but not the DIBL. There is another effect which can happen because of the traps. Traps uh, are these impurities, electrical or physical, that happen in the oxides, which tend to impact the dependence of this drain current versus VG in a non-linear way. And hence they could impact some part of the curve, say here, more than what happens on the top part, right? And they can affect the subthreshold slope more than they can affect, say, a DIBL. Then there is one more effect which is very prevalent in FinFETs, which tends to affect the subthreshold slope more than it affects the DIBL. And that effect is called the subfin leakage, right? And this is a very important thing to control. So I will draw the FinFET again in this fashion. And I'm showing the gate that is surrounding the FinFET. And this is the gate oxide, right? And the source and the drain, the source will be, say, coming out of the board, the drain would be going into the board. So if I were to take a cross section of this picture, right, and what I would see is the gate looks like here, the source would look like here on this side, the drain would be here, this would be the gate, and if I draw here, this point is being here. This is the region which is controlled by the gate because the gate is wrapping around the fin. And this region is the part which is, so let me draw it here, would be this one, right? Now, think about how the gate is able to control this region very well because it being a FinFET device, and the source and the drain leakage is very well controlled. However, in this cross-checked line area, the source and the drain are free to talk to each other because the gate has no control. And this leakage is one of the most painful things to control in a FinFET, and that is one of the things that can impact the subthreshold leakage by the subthreshold slope was coming down nicely and then it just flattens out, which means it doesn't end up reaching the leakage that it needed to reach because some current just kept flowing through this part. Correct? This is one of those things which affects the subthreshold slope much more than it affects the DIBL. Right? Now, what are the things that impact the DIBL more versus the subthreshold slope? And those things are related to the on state of the transistor, right? Which includes things like mobility of the transistor in the on state, source drain resistance. So anything that impacts the on state tends to impact DIBL more. It also is dependent on the choice of the current that was used for this effect of DIBL. And most of the times, the currents that are chosen for DIBL are higher than what we end up picking for subthreshold slope. So that's the reason why it ends up picking these on-state properties of the device. It's not guaranteed that a DIBL has to be taken at this point. It could be taken much lower as well. In that case, the on-state properties will not affect DIBL, right? So now the next point about these effects is, what is their temperature dependence, right? Temperature dependence is an important feature, and it's important to know to understand the temperature dependence of the subthreshold slope. Say, it's important to know how is the current flowing in the off state where these things are being measured, right? So if this is your log ID versus Vg, right, and this is where the subthreshold slope happens. In this part of the curve, which is called the off state, as I drew before, the carriers are going are are kind of leaking between the source and drain, even though there is a barrier between them, and that leakage mechanism is being driven by what's called the diffusion current, right? And diffusion current means that diffusion current is something which is less dependent on what the electric field is between the drain and the source. It's more dependent on the fact that if there are more carriers on one side, they're just going to invariably spill into the area which has less carriers. And they're being dominated by how much energy those carriers have, right? So if they are very energetic, they would tend to hop over this barrier more easily, right? And what we say is that ID in that off state condition is dependent on the barrier, which is say this phi b, right? Negative that and divided by kT. So higher the temperature, more is the ID. Lower the barrier, more is the ID, right? Now, if we were to do some math on this, what ends up happening is that take a log on both sides, log 10 of ID, phi b, and this becomes proportional to kT. This is just a constant, and this is the temperature. What we also know is that the change in the barrier, or we can say change in the gate voltage versus log of ID, is also the subthreshold slope. And that is directly proportional to the temperature. This is a very key effect, right? In fact, the subthreshold slope is a very good measure of the temperature testing of the device, right? So what this means is that if that device were taken in a cryogenic temperature or very low temperature for quantum devices, the subthreshold slope will go down. Going down implies it will become much sharper on this scale. So let's draw this. So if this is how the subthreshold slope used to look like for room temperature, if we take it in a cryogenic case, it's going to become much sharper. What that implies is, so this is the subthreshold slope becoming low because it's the opposite of this slope. And this is what it impacts on the off state. So this is low temperature and this is high temperature. And this has huge implications, right? The off state current has dramatically decreased just because it has gone to a low temperature. And physically we can understand because the diffusion current has reduced because the carriers don't have enough thermal energy to be able to hop over the barrier, right? So that's what happens with the subthreshold slope versus temperature. It's linearly dependent on temperature, and it's a very good metric. However, if you look at the DIBL effect, there is no real direct correlation of temperature with DIBL. It could go up, down, or not change. There is not a huge dependence because DIBL is the difference between the two drain voltage cases, and that's why it's not a sensitive metric for temperature. Okay, so the one last point I wanted to mention was these short channel effects, they are much more impactful when the drain voltage is on the high side versus when the drain voltage is, say, on the low side. And this is what makes them even more impactful because the high drain voltage is when the device is saturated, right? And the channel part matters more. And when the channel part matters more, the subthreshold, the short channel effects also are bad. So they end up making the overall device much worse. Whereas in the linear region, what happens is we tend to get more diluted by things that happen outside of the channel. So here, this would be the channel, this would be the source resistance, this would be metal resistance, right? And this is again our metal, this is the drain resistance. So in the linear regime, which is where the drain is low, this R channel gets diluted much more by these components. When the drain is high, the R channel starts to matter a lot more when the transistor is saturated. I will talk about this topic much more, but for this point, it's sufficient to say that the short channel effects um, are hugely impactful in the high drain case. And also because in the high drain case, the short channel effects appear more and their impact is also more. So both of those things make it a worse proposition for high drain voltage. Okay, so um, that's all for today for this topic. Thank you, folks.